sure you want to start the light event now?
Yep. All right, and we went red, so I think that's good. All right. Can you? Yes. All right. Welcome to our June Science Friday. Thank you to the Friends of Alderman Creek. If you're live and in person, you can have some refreshments. They sponsor all of these Science Fridays. The next one will actually be in August. We typically take July off because it always runs into the holiday. And our August one will be interns to see what they've been up to this summer. They have just started, so a little bit of panic just over there. Still 2 months away. And I'm gonna have our research coordinator, Dr. Steve McMurray, introduce our speaker for today.
Pleasure to introduce our new Margaret A. Davidson Fellow, 2024-2026, Mike Back. Mike comes to us as a PhD candidate from Kent State University. He completed his Bachelor of Science at Kent State in 2021, majored in biology with a Spanish minor, graduated summa cum laude with honors. As an undergraduate, he conducted research on the effects of reclamation on soil properties at legacy non-coal surface mines. And as part of that work, he actually wrote it up, and is it published yet?
Yep, yeah.
And it recently was published in a peer-reviewed literature, which is really impressive for an undergraduate. He subsequently moved on to the PhD program at Kent State, where he is a member of Lauren Kinsman Costello's biogeochemistry lab. He has a leadership role in the lab, mentoring undergraduate students, some of which are co-authors on this presentation. Also, importantly, he's been a leading member of the H2 Ohio wetland monitoring group. And as part of that, he's taken a lead role in assessing the nutrient budgets of these 4 wetlands across the state, and really become an expert on nutrient fluxes across the sediment surface water interface. Michael,
all right.
take it away.
Thank you. Well, thanks for the great introduction. I didn't send you any of that stuff, so you must have pulled it from earlier resumes I sent you. I was like, whoa, okay. Cool. Yeah, great. Yeah, like Steve said, I'm a PhD student now. The stuff that I'm presenting on today is going to be a mix of some biogeochemistry and general information that I've been gathering, and then dive into a presentation that I just gave at the International Association of Great Lakes Research Conference in Windsor a couple weeks ago. So I'm going to share some of that data, and that's all kind of culminating into a first chapter in my dissertation research. So this is a nice, beautiful picture of Magee Marsh Wildlife Area, which we'll get into a little bit more later. But I just want to go into a little bit of Biogeochemistry 101 for those of you who may not be as familiar with what's happening in a wetland. You have this constant cycling or the circulation of phosphorus and nitrogen within these wetlands, along with many other macro and micronutrients and trace elements. But the main focus of my talk today is going to be on this phosphorus and nitrogen. We'll talk about why in a little bit. But in general, I want to look at some of these phosphorus cycles, this phosphorus cycle and then the nitrogen cycle after that. You have these different boxes of phosphorus, these different forms of phosphorus that are living or they're not living. They're positioned in different areas of the wetland. And each of these boxes represent pools of this element, phosphorus. So in the central pool there, you have phosphate, PO4 3-, and that's the most readily or labile or mobile form of phosphorus, easily taken up by microbes and plants, and then can be taken up further from that by other organisms. And then below that, you have organic P, organic phosphorus, which is once it's taken up by those microbes or plants, it's stored in them and then can be broken down by other organisms. You also have forms of P in the rock, and those are kind of the more lasting forms of phosphorus. Those are locked up in the rock material and are less available to organisms. And then you have phosphate that can bind onto metal oxides or clay particles within the soil or the sediment, And then you can also have P that's bound onto calcium carbonate in the soils. So all these different elements and all these different forms are working together and exchanging between each other. And between each of these pools, you have these arrows or these fluxes. And those fluxes represent that change. And it's usually in some sort of rate that we think of that change. So up at the top from that rock P, you have weathering, broken down phosphorus from the soil, gets turned into that dissolved phosphate form. And then you can have the precipitation out to calcium carbonate, or the sorption, that's that binding factor onto the metal oxides there on the left side of the screen, or onto those clay particles. And then of course you have that immobilization or the uptake of P into organic material. And then those can also exchange back into that phosphate form, and they're constantly fluxing in time and in space within these wetland systems. Nitrogen cycle also has these fluxes and these pools, but it's a little bit more biologically mediated. You have fixation of nitrogen from the form of gas, which is all around us in the air, and that fixation is really taken part by organisms, a lot of times in the soil, that are fixing that nitrogen and turning it into organic forms of nitrogen. And then similarly, you can have that organic forms broken down by other bacteria in the soil or plants as well, and turned into a more mobile form of nitrogen like ammonium. And that ammonium can go through some processes via nitrification and change into nitrate, which is a really big buzz molecule, like buzzword for nitrogen. A lot of this fertilizer that we're applying out in the fields are that nitrate or ammonium, easily taken up by those plants to allow them to grow. And then kind of to close the loop here, you have that denitrification action of changing that nitrate into a nitrogen gas, so kind of releasing it back into the atmosphere. When we think about wetlands, we think that they're really good at denitrifying. You have a lot of water that's sitting over, and that anaerobic status under that water and in that sediment can spur on that denitrification and allow it to convert that nitrate into N2 gas. I added this Haber-Bosch process here, which is a really important flux that's happening. It's us humans taking that N2 gas and turning it into ammonia. So unlike the natural processes that are happening out in the soil, we are now changing that gas into ammonium and allowing that to be spread onto our fields and allow that growth into our crops. And I don't mean now as in just now. This process has been going on since the 50s, and they've been able to use these forms of nitrogen to increase yield, which is really important for supporting this large population. So why are these specific forms of nitrogen and phosphorus really important? Well, I kind of said before, these forms, nitrate, ammonium, and phosphate, are really bioavailable. They're easily taken up by plants and microbes. So like I said before, you can spread that over your crop fields and you have crops grow up. And then similarly, if those crops eat up all that nitrogen and phosphorus, you can have a little bit less yield or less growth in your fields. So what happens is we turn that nitrogen gas into ammonium, and then we spread that on our fields and allow more growth. Unfortunately, it can allow growth in other systems other than just the farm fields. And we're all too familiar with harmful algal blooms that are occurring in Lake Erie. And that's in part driven by some of this fertilizer that's being added to the fields that's flowing down through our streams and rivers and ending up in the lake. And then that algae, just similar to the plants, are taking up that nitrogen and phosphorus and blooming and creating massive biomass in the lake that can sometimes be toxic if it's the specific type of bacteria. And just to kind of spread that point a little further, I like this map from the EPA showing how much agriculture there really is. This is specifically the Maumee Basin. So a lot of that agricultural runoff, this brown area you're seeing, is being pushed in through one central area and flowing out into that western basin of Lake Erie and spurring on some of those harmful algal blooms that are raging. And boom, another scary picture of a hat. Luckily, we have a lot of initiatives going on right now to help mitigate the spread of that sediment and that spread of that nutrients that are flowing into our streams and rivers. In particular, some of the Great Lakes Commission is doing some of these reduction programs to help mitigate those nutrient releases. The EPA is working on that. And we also have H2 Ohio, which is a huge initiative set up by the governor and run by the OhioDNR and Ohio Department of Agriculture and the Ohio EPA as well, all combining to work to better that water quality in not just nutrient aspects, but in all aspects of water quality throughout the state. Is anyone here familiar with H2 Ohio? I know at least a few. couple, cool. Well, for those of you who aren't super familiar, like I said, there's a bunch of different branches in the H2 Ohio initiative. One of this branch is reducing phosphorus. That's where they're kind of coming to the source. They're coming to the agricultural fields and they're trying to implement new best practices to reduce the runoff of phosphorus and nitrogen from the farm fields themselves. Another part, which I'm a big participant is the creating of wetlands. The ODNR is working together to buy up land and to promote the building of new wetlands throughout the state of Ohio to help mitigate that nutrient runoff into the lake as well. And then, like I said, there's also other parts that are unrelated to nutrients that are trying to fix water quality on a broader spectrum, septic systems, and replacing those lead pipes that are contaminating water right now. So like I said, the wetlands is really a part that I'm invested in. I've done the last 3 years of my PhD really interested in a lot of these wetlands and digging into some of the nutrient processes that are happening specifically at those. And so I mentioned the H2 Ohio initiative is this broad initiative that the governor set up. ODNR is then going through and purchasing either the wetlands or they're funding projects that are purchasing wetlands or building wetlands across the state. And then the Lake Erie and Aquatic Research Network, LEARN, is coming through and monitoring all of these wetlands, or all, quote unquote, of these wetlands that are being built by the ODNR. We're doing our best to monitor them all, but as you can see, this map is outdated even. We have over 170 wetlands built already after 3 years, I think, that the program's been going on. And some of them here are highlighted that are complete. But like I said, that was back in October, and there's already 20 or so more that have been added to the map. So we're making great progress. The monitoring program specifically is a branch now off of that wetland program that is in charge of determining how well these wetlands are working, how well these wetlands are filtering out nitrogen and phosphorus from the water. And to do that, we need to think about these wetlands in these different categories. And so we read through a lot of the literature, and they started to develop these categories of flow-through wetlands, coastal wetlands like we're sitting on today that are exchanging water with the lake, a floodplain wetland maybe that's adjacent to a river or a stream that floods up in times of storm events, or depressional systems or isolated wetlands that don't have a main inflow or outflow of water, but do have some significant source of contributing to that nutrient retention over time. And so I said we branched these out into 4 different areas, but that's not necessarily true. These wetlands are completely different from each other. 170 wetlands into 170 different boxes, different types of wetlands, because they're all unique in their own way. And it's hard to isolate just the hydrologic inflow or outflow of each of these wetlands. So this is a picture of an isolated or depressional wetland that we have near Trumbull, Ohio. And that's my advisor there, Lauren. We were out on a snowy day and got to run around the new or baby wetland that was created there. No vegetation anywhere, but it was recently dug up and made into these pools. And it's an isolated wetland, but it also has a central outflow that flows out. So it's not acting quite like an isolated wetland. So it's unique in its own way. And then this is a coastal wetland, but it's a really different coastal wetland than what we see here at Old Woman Creek. This is a diked coastal wetland at Magee Marsh Wildlife Area, where you have these large earthen barriers that are separating the stream here on the right side and the wetland there on the left side. And the restoration aspects are creating a new pipe that allows that water to flow freely in between the two. So how are these wetlands working in a nutrient aspect? Well, the water and the nutrients flow into these pipes or flow into the wetland. They start to settle down. As you can see, a big plume of sediment going into this going in from this pipe here. Sedimentation starts to act, and that sediment starts to settle out. That's holding a lot of that nitrogen and phosphorus. And then plants are able to take up those nutrients. Microbial immobilization occurs and is changing those nutrients into different forms, maybe changing nitrate into N2 gas and allowing that gas to be released to the atmosphere. But wetlands can also be sources of nutrients. In some instances, if you have big rainflow events, it can spur the sediment, kind of cause it to resuspend, and then that water can be washed off and potentially contributing to nutrient sources downstream. And so we start to think about these wetlands and how to classify these wetlands in this mass balance approach. And it's easiest for us as academics to make this big box and think of this wetland as a big box. And we think about everything that's going into this wetland, all that nitrogen, phosphorus, and then we calculate all that nitrogen and phosphorus that's going out of that wetland. And it sounds pretty easy, but as you guys have seen here at Old Woman Creek, there's many inflows. There's not just one central pipe that's leading into the wetland. And then sometimes even here at Old Woman Creek, you don't have an outflow. You have that beach get blocked up. And then what happens? How do you calculate anything after that? In general, though, if you think about more nitrogen and phosphorus coming in and less nitrogen and phosphorus going out, you think of that wetland as a sink or a net retention of nitrogen and phosphorus. I put that in green because a sink is good. It means we're taking those nutrients out of the waterway and we're leaving it in the wetland and allowing maybe cleaner water to come out, or slightly cleaner water. Like I said, wetlands can be sources too. So if we're measuring all this stuff going in and we notice that there's more nitrogen and phosphorus coming out than there is going in, then that wetland can be a source. And that's also not to say that all wetlands are always sinks and all wetlands are always sources. That can change in time. Your seasons can vary, which changes the amount of water going in and the amount of water going out. And I made that big box, but there's also arrows that are happening within that box. And specifically, you can have this exchange of nitrogen between the atmosphere and the water. And then you can have some from the sediment down below into the groundwater. And then this gold arrow is where my talk is going to be centralized for the rest of this time. And it's that exchange of nutrients between the sediment and the water. And that's a key exchange to acknowledge and to measure, because those nutrients that are going into the sediment, we kind of classify those as ones that are being locked in or banked in the wetland. I don't want to dig too far into this image. This is an image from the H2 Ohio Wetland Monitoring Program. And there's a lot going on here, but I just wanted to highlight there's a lot of different ways that we can measure nitrogen and phosphorus throughout the wetland, including measuring the vegetation, cutting it up, and measuring what's inside each of those. We measure what's coming in from the water, what's already in there from the sediment, or what's leaving from the water. And we're able to isolate a lot of these arrows that are occurring in the wetland that are exchanging those nutrients in all these different fashions. So a lot of time, a lot of money going into this, and I'm just one centralized or one tiny part of this whole project. So we all here recognize the importance of coastal wetlands. There are these critical transitional ecosystems between our streams and lakes and the terrestrial bodies, and they're really important for wildlife habitat, for vegetation habitat, flood control for neighboring communities, and then of course water quality, which is obviously a focus here today. And the structures of all these wetlands can change in time and in space as well. So here's a couple pictures of Old Woman Creek, beach open and beach closed. And I really like taking these simultaneous pictures, and I got to get those wildlife camera pictures to see that over time too, because that you guys all know it can change so rapidly within a day even to open and close, and that obviously changes the amount of water that's going out of the system or coming in, and can affect the nutrient processing that's happening in the sediment. And these wetlands across all of the Great Lakes are extremely variable in their land use in their neighboring watersheds. So what kind of water is coming into each of these wetlands are changing. You can see a lot of Lake Erie is that red and orange. The red and orange is going to be urban and agricultural systems, whereas up in Lake Superior, you get more of the forested or prairie systems, more green. And so to hammer on H2 Ohio one more time, 11 out of the over 170 wetlands in H2 Ohio that are built are these coastal systems that are being reconstructed. And now we're kind of stepping out from Old Woman Creek and we're stepping back into the dike systems, because a lot of the wetlands that need restored here along Lake Erie in Ohio are diked coastal wetlands. They're not these natural systems that are flowing through and allowing that exchange of water. So here that earthen dike is separating those two, and then H2 Ohio or ODNR comes through and they insert this water control structure that allows water to flow in and flow out of the wetland. But that is being actively managed by people that are managing that land area. So there has to be a person that's out there opening up that water control structure, letting the water in, and then closing it. And that's an important factor we'll talk about later, because wetlands can only retain nutrients if more nutrients come into the wetland. If there's no nutrients coming in, then they can't be a sink or a source. They're just kind of sitting there and being a pond. So I mentioned Magee Marsh Wildlife Area, and that's where my study has been taking place for the last couple of years. You can see up here, it's kind of near Port Clinton area, and Magee Marsh Wildlife Area is the larger area, kind of next to Ottawa National Wildlife Refuge. And then I'm focusing in here on Turtle Creek Bay, which is just one earthen cell barrier of that whole wildlife area. And these red dual arrows here represent 2 water control structures that were implemented into this wetland with the H2 Ohio funding. So the restoration solely took place at those 2 structures and allowed that reconnection. And so let's dive into the sediment of this system a little bit. We've talked about the nutrient cycling, but within each of these systems, you have these different pools of nutrients in the sediment and in the overlying surface water. So you have mobile nitrogen and phosphorus up in the surface water, maybe dissolved, and then you have that same mobile nitrogen and phosphorus dissolved in the pore water of the sediment. And then you can also have these fluxes between these different pools of the elements within the water column and the sediment. You have that binding, that sorption onto clay particles in the sediment, or you have the uptake and release into organic matter, organic NNP, both in the water column and in the sediment. And then over time, you have burial of that organic material deeper into the sediment. Specifically, my work here is looking at this interface, like Steve said, between the sediment and the overlying surface water, and understanding that rate of retention, that green arrow going in, or that rate of release, that orange arrow going out of nitrogen and phosphorus from the water column to the sediment. So I had a couple questions in mind in this study. I wanted to know if vegetation type in the wetland and water nutrient concentration affect this exchange of nutrients between the sediment and the surface water. And how do these different methods that we can measure sediment surface water nutrient exchange vary in an inundated system like Magee Marsh? So there's a couple different techniques that we use to measure nutrient exchange in the wetland. One of them is to take these soil cores, where we go into the field and we take a clear piece of PVC and we take some of that sediment and we bring it back to the lab with us. And we also bring back some inflow water, which is just some water from out there at the wetland collected with a little cube jug. And we allow that water to run pumped into this core, and it drips out into this sediment core here, right at the sediment surface water interface. And then that water eventually gets pushed out through an outflow tube and into a sample. So what's happening is it's slowly accruing water in this core, and then about every 4 hours, all of that water is eventually being pushed out of the core itself and into the sample. And what we can do with that is to measure the outflow concentration of nitrogen and phosphorus, and we can measure the inflow concentration of nitrogen and phosphorus and subtract the two, multiply it by the flow rate, how fast that water is moving in through the core, and divide that by the whole surface area. And what we end up with is this flux in milligrams of your nutrient, nitrogen or phosphorus, per meter squared per day. So an areal and time flux of that wetland sediment. And so this is what it looks like when it's set up in the lab. One of my undergrads did one of these experiments last fall as well, and then she drew this beautiful picture for me, because this picture kind of looks like a lot's going on at one time. But you can see right here and right here is that jug of water that we brought back from the wetland. And then these are all the cores that we have setting. And then the peristaltic pump is sitting in the background here. And then that tube kind of follows the direction of the water flow and eventually dumps out into that larger bucket where we collect little sample cups for each of the outflow samples. And this is a great method to measure nutrient flux. But what we're doing here is kind of isolating some of that sediment from the rest of the wetland. So we can understand kind of the mechanisms of what's driving this nutrient flux, but we don't know how all that maybe groundwater or animals in the wetland or vegetation in the wetland are acting on that sediment as we measure that flux. And so in order to do that, we also implemented an in situ or an in-field experiment where we made some stacked resin bag cores and stuck those out in the wetland. And the way these cores work is you have these little bags of mixed bed ion exchange resin, and that resin is similar to resin that you'd see in like a Brita filter or a water filter. And those little beads that you can see right here are filled with either H+ or OH- ions, and those beads act strongly to grab onto any molecules that are flowing past the bead. So like phosphate molecules, nitrate molecules, or ammonium in the water or in the sediment is going to be attached onto those little resin beads and then not able to be released. And so what we can do is stack 3 of those bags on top of each other and stick that out in the mud for a couple weeks. And then when we retrieve it, we can measure exactly how much nitrogen and phosphorus is on each of those beads in those bags. And then we can subtract the top bag accumulation from the bottom bag accumulation and divide that by the surface area and the days deployed. And we get the same measurement of nutrient flux per meter squared, of milligrams per meter squared per day. And so kind of give you guys a picture of what's happening. If there's more nutrients flowing into the sediment from the surface water, we'll see more nutrients on this top bag. If it's vice versa, if there's more nutrients flowing out from the sediment, we'll see more nutrients accumulated onto that bottom bag. And this method is in situ, so we stick it out in the wetland and we leave it out there for a couple weeks. So it's really capturing all of the fluxes, all of the equilibrium or lack thereof that's happening in each of the wetlands that could be associated with vegetation or bioturbation or anything that's happening in general in the field. So a couple pictures of what these bags look like when you stick them out there. They're pretty small, about 3 inches in diameter, and you can go and stick them in areas that are dry or areas that are flooded, and you leave them out there for as long as you want in the field to allow that accumulation of nutrients. Early on in the experimentation phase of these, we noticed that sometimes animals like to dig in them, so we had to be careful about where we were placing them and if we were noticing repeat offenders in a certain area. But you can see here each of those little bags kind of got ripped into, and I don't think they were eating anything. I think they were just curious on what was placed out in their wetland. So at Magee Marsh, we separated this wetland into large vegetation patches. Each of those are kind of marked here in the colors, and you can see them listed here on the bottom here. So the large swash, this light blue, is floating vegetation. Mainly in this wetland is lily. We don't have a lot of locusts there. And then we have some emergent vegetation on the edges, mainly just this patch over here, and that's like grasses or forbs. And then we have hardwoods along some of the other edges of this wetland. A lot of willow species here at Magee Marsh that are kind of growing emergent up from the flooded areas. And then occasionally you have this submerged vegetation where it's kind of a lack of arching water on the surface and is just deeper water. And then you have another large patch of typha there in the center cattail. And we deployed stacked resin bag cores at each of these triangles, and we also took those intact sediment cores from each of the triangles. So we have a really good paired study at each of these sample points across the whole wetland with both of these different methods of measuring nutrient flux. So we also did the west side in 2022 and the east side in 2023. This wetland is huge. It's about 1.5 miles stretching from end to end. So a lot of kayaking through a lot of the dense lily got tough and allowed us to only do part of the wetland in 1 year. So the next few slides are going to be some of the data that I've collected. So we're actually getting into some of these nutrient fluxes. So I want to orient you guys to these graphs first. On the y-axis is that flux rate in that milligrams per meter squared per day. And right now we're going to look at phosphorus, and then we're going to look at the different forms of nitrogen. On the x-axis here, we have those vegetation patches aligned on these bottom pictures. And then that zero line, that dark line across the middle, that represents equilibrium. There's no flux from the top going to the sediment, and there's no flux from the sediment going into the water. It's kind of a net zero. And then anything that's above that zero represents a release, or orange. I put orange for bad for some reason. But a release of nutrients into the surface water, and then a retention or an influx of nutrients into the sediment will be a green box, and it will be below that zero mark. Anything negative is good, the sediment's locking in. Anything positive, it could be bad. Yeah.
I think you do.
Yeah.
You want it to stay in the ground.
Mm-hmm. Yeah.
That's where, okay.
Yes, yeah. No, that was a great question. Yeah, the green here is good. So anything that is being retained by the sediment, you could think of there be a little bit more of that processing going on, perhaps denitrification in the layers, allowing for nitrate to be used up. And similarly, phosphorus can be kind of immobilized into the sediment a little bit better, locked in there. It's kind of like a bank. If it's in the sediment, you can think of it more as a bank. That's not always the case. It changes in time and it changes in space. But as you can see, it's a little variable. So with these intact sediment core incubations, we saw some of those green boxes here in the emergent and the submerged vegetation. There was more of a net retention of that phosphate, but the hardwoods there was really releasing a lot of phosphate over time. So we could think that in hardwoods patches, perhaps that phosphate was being released into the water column, and that would be bad because the water column could potentially take those nutrients out into the lake afterwards. When we did the same experiment in the field with those stacked resin bag cores, we saw a little bit more of that net zero effect. The hardwoods were still releasing some of that phosphate, but now emergent vegetation and Typha are kind of more at in submerged are kind of more at equilibrium. I'll notice a couple points here are outliers here, and this point that's super negative or more of a retention. That was right next to that water control structure, and there was water being pumped in. A lot of those nutrients were being pumped into the wetland, and we saw a net retention or a sink into the wetland sediment at that one point. The opposite was happening at this point here, where a lot of that sediment was releasing phosphate. So with nitrate here, and the intact sediment core incubations, there's more of that net zero, less variability across the different vegetation patches. But now we're seeing a little bit more variability within a vegetation patch in between the two groupings. And this is a kind of weird bimodal or two grouping data structure that we're getting here. And I'll dig into that in a couple slides when we talk about that inflow water that's flowing into the cores. These two groups here had different concentrations of nitrate, so that's kind of what was driving that difference in flux values. We still do see emergent vegetation here, and now Typha as that being that net sink of nitrate in the sediment. When we do this in the field with the stacked resin bag cores, again, pretty net neutral or an equilibrium in the field. And again, it's not that there's no flux happening between the sediment and the surface water, but over time, that flux is pretty steady between the two different layers. We're not seeing this large release or this large retention of nitrate in the sediment across all of this Turtle Creek Bay wetland. Ammonium is a different story. If you look at this y-axis here, a lot of these values are positive, and they're at a higher magnitude than any of the other phosphate or nitrate fluxes that we've seen so far. So a lot of these patches are releasing nitrate in these intact core, ammonium in these intact core incubations. That's not too uncommon. I said that those intact cores are kind of isolated mesocosm type structures. And what can happen in those isolated systems is that the oxygen can be used up, and then the nitrification can't happen. So that ammonium going to nitrate can't occur. And so you have this ammonium being released from the sediment. It's good news to see that when we do this in the field, we don't see that same efflux of ammonium. If even there's a little bit of retention of ammonium within the hardwoods and perhaps the emergent vegetation. So a lot of that ammonium is being taken up either at that fine scale sediment surface water interface or by some organisms below the sediment as well out in the field. So I wanted to look specifically at how this inflow water concentration was affecting the nutrient flux. And that's important because if we can see how that flux is changing in relation to the surface water, we can try to best estimate how the wetland will retain nutrients over time. So this graph here still has flux on the y-axis in your milligrams per meter squared per day, but now you have the inflow phosphorus concentration on the x-axis. So how much phosphorus is really in that inflow water that's coming in. And so what we see here is a negative trend line. And what that means is as you have more phosphate in that surface water, you have more inflow into the sediment, so more of a retention. And that's super good news for Magee Marsh. That means if we allow more water with phosphate into the system, that the sediment can keep up and it can retain more of that phosphate and suck it into the sediment and maybe bank it over a longer period of time. If we saw that reverse, we'd think that maybe Magee Marsh was a source of nutrients now instead of a sink. We see that same trend with nitrate being a sink with increased inflow into the sediment. And just to explain that bimodal data structure that we saw before, some of these different inflow concentrations were higher in one patch and then lower in that same patch. It's kind of a thing with water where you can take a water sample from here, you can take a water sample from a point a foot away, and they can be completely different. And it's just kind of the luck of the draw that you're getting. And that's what was happening there. But it's good to see that those are still following the same trend of a negative or an inflow into that sediment for Magee Marsh. Of course, with our ammonium, we didn't see that same trend, and that makes sense because all of the different vegetation patches were releasing ammonium into the surface water. Yeah.
At some point, it can't take anymore?
Yeah.
Then what?
Yeah, exactly. That's a good point. And that's kind of what we're seeing here. It's not super saturated. And in some cases, what we would see if it was super saturated is a positive trend line. So if you increase, or maybe a net zero trend line, if you increase that inflow concentration, you'll see no influx into the sediment or a release from the sediment. And that's what we expect to happen in some of these wetlands over time. As they build up phosphorus and nitrogen, they could potentially start to release phosphorus in the water column. And then that wetland, what you would do would be more of a management question of, would you dig that wetland out so as to allow it to sediment, allow more sediment in? But yeah, that's a great question, and it's something that a lot of people on the best management practices side of building these wetlands are trying to dig into now on what they do later in the life of each of these wetlands. Right now, it's a little early for us to tell. They're all being built now, so we can't necessarily say what's going on. But that's a great question. Yeah, this is good news for Magee Marsh, though. It means that these soils can still retain some of those, and that's what we like to hear. I also learned that maybe classifying nutrient flux based off of that inflow concentration is a better way than the vegetation patches. That may have a more impactful control on the flux. But I also want to highlight here that our work at Magee Marsh can help inform some of the management that's going on at this site. So maybe if I let them know that these vegetation patches are retaining more nutrients, they could select for that vegetation within the wetland. Or if we think about this more across time, if there's a time when they could open or close these water control structures to allow more water in or out, we could help inform them on those decisions. This is all leading to a combination of what did Magee Marsh do in 2023? And this is the big one-liner we like to give, is that it didn't retain any nutrients in 2023 because the water control structures were shut the whole year. They were doing a lot of maintenance on this wetland. So they were rebuilding dikes and kind of changing things up. So no water was able to come in at all. But what we did show is that even though water wasn't coming in, there was still that exchange of nutrients within the sediment and the surface water that was occurring even without new nutrients coming in. So that kind of wraps up most of my stuff that I presented on so far at IAGLR and some of my dissertation work as well. So I just want to shout out some acknowledgments to all the funding. H2 Ohio was a big funder for this work, and ODNR, and then Learn, as I'm a part of as well. It's a free network to join, so if you're in academia, feel free to join in. And then a small grant from the Herrick Society at Kent State helped me out as well. There's a lot of work that went into this project, a lot of time in the field, a lot of hauling boats around. I love this picture of our undergrads rowing here across this wetland with this Learn photo figure on the back. And then some of the stacked resin bag core deployments involved me diving in and getting down to the depths of the wetland and installing these little cores. So I ended up with a lot of duckweed all over my hair. It was a good time. So I just wanted to kind of give you a preview here at the end. We're running up on time, but I am going to be the next Davidson Fellow here at Old Woman Creek. So I'm going to be here for the next 2 years doing some work here and there, mainly about nutrient processing that are occurring in the sediment. So similar stuff that I've done so far, but now I'm kind of digging into the natural wetland side of things. So for my project, I've set up a couple of transects that I've wanted to investigate here along the inflow or the outflow of the wetland, kind of the middle of this wetland, and then towards the inflow as well. And each of these kind of transects different hydraulic residence times in the wetland. So how that water is interacting with areas of the wetland that are kind of back or in coves, and how that changes maybe the exchange of nutrients between the sediment and the surface water. So I'm going to try to set those up and get also a baseline of the sediment conditions at Old Woman Creek. We don't do a lot of sediment sampling here, but I'm going to change that in the next 2 years. We're going to get a lot of soil in here. Yeah, and I'm going to try to do this across time as well. So across the different seasons and in different times of when the barrier beach is open or closed. And I expect that to change. I think the influxes of this wetland will be highest near the inflow where all that nutrient-rich water is coming from. And we already have some sampling that's been done here near the barrier beach where we installed some of these stacked resin bag cores. And what was most promising about this data, we haven't been able to dig into it. We don't have a ton of replication in time here. But what's super interesting is across even a few like tens of meters here on these different sampling points, you see extremely different flux rates occurring at each of these sample points. So one here is this point that's nearest to the beach, and it seems to be a net sink for phosphate. But if you go just probably 50 meters away, if that, to the sample point 3, you see a net release of a ton of phosphate. So I'm interested in knowing what's kind of driving that change, that variability in flux in Old Woman Creek, and how that's changing in not just phosphate, but also different forms of nitrogen as well. And like I said, that barrier beach open and close is a huge factor here. So I'll want to dig into that a little bit more too in the next 2 years. So that wraps up everything I got. Feel free to take questions if you guys have any, but appreciate you letting me come out and speak to y'all. Yeah.
Fish and other animals that are in the water can disrupt the sediment. I mean, we see so many carp and catfish. Is that going to be like factored in? It's like a potential, I guess it would be increasing the sediment.
Yeah.
Correct?
Yeah, absolutely. Yeah, that's why I like to use these stacked resin bag cores too, because they're out in the field and they're really telling you what's happening in the wetland with all of those different components. In the past, a lot of these core experiments, you have that absence of those animals, that especially the carp that's playing a big role here, but also any of the vegetation that's also playing a role. So yeah, I would expect that resuspension of the sediment could lead to maybe some effluxes or releases of nitrogen and phosphorus into the surface water. But also you could have that resuspension in one day and then a settling in the next day, and maybe there's more of that equilibrium that we'll see over time. And I'm not too familiar with where the carp specifically are. I know every time I go to the outlet, there's a ton of them there. So maybe that area would be more affected than some that are further up in the wetland. But yeah, certainly good question. Cool. Yeah.
Questions in the chat.
Sounds good. Cool.
Michael, when do you think you'll do your first like install?
Yeah. I think I've planned it out for the spring and summer of 2025. So next spring and summer will be the first installment of the course. So you're looking out for me diving into the
It's going to be
wetlands.
done one deployment. Well, actually, two now.
Yeah, too. Yep. Yeah.
How did you mention this to? How do you use it? I put like.
Yeah, that's a great question. There was a lot of trial and error with these cores, and it certainly depends on the concentration of nutrients that are flowing through your wetland sediment. So an area like Magee Marsh is pretty void of both nitrogen and phosphorus. It's kind of isolated from the system unless there's a lot of nutrients flowing in. So we left them out for 10 days. I think the first time I left it out for 14, and some of them got oversaturated with nutrients. So we cut that back to 10 days, and that seemed to work for us. Here at Old Woman Creek, though, there's a lot more of that water that's coming in from agricultural landscapes. So there's a lot more of the nutrients in the water column. So I think our deployments were only 5 days here. And that was a trial. I think I'll do more trials in the future to see if we could leave them out for longer. But yeah, it's kind of seeing how long they last. Unfortunately, each of those cores cost like $30. So to just trial and error them, it sucks to throw them out there and lose a core if it oversaturates due to leaving it out for too long. But yeah, that's a great question.
Go ahead, Zoe.
Go for it. Yeah, I didn't write in doing the cores for the Davidson Fellowship. The thing about the cores is that they don't cost really any money. They cost my time, and that's it. They're about 72-hour incubation, so I'm up all day and all night attending to them. But they don't cost a lot of money. So if we decide that that's something that would be beneficial to guide like the mechanisms or understand the mechanisms of the flux a little bit more, it could be worked in probably, but it wasn't in the original plan. Yeah. I don't know. I don't think I'd put reliable on it. Probably they're telling a little bit of a different story here, and they're kind of telling that the story that's different is an important difference. Those isolated cores are telling maybe something different on the shorter term, or specifically what the sediment is doing. Whereas when we leave them out in the field, it's kind of letting us know what the wetland as a whole is doing. And all those different components are weighing in. So yeah, maybe not reliability is the question, but it's certainly a different kind of understanding of what's going into these. Yeah.
In another realm, be great for farming. I mean, I'm thinking of river farms, you know, and that's all sediment, but that's wonderful, wonderful farmland. So is that an option maybe to dig out this sediment and bring more in and sell it as organic, wonderful, whatever?
Yeah. No, that's certainly, I mean, it's not an option in some of these areas, like the protected wildlife areas, obviously, but in some of the H2 Ohio wetlands, that's certainly been a question in the management. Like, can they dig it out and probably not sell it, but give it to the farmer that's adjacent to them or something to cut down on, moving a lot of that dirt is expensive itself. But I know that I think John Witter was here before and gave presentations. He's a researcher at Ohio State, and he does stuff with the 2-stage ditches that are being implemented on farmlands across the state. And what happens with those ditches is they can start to accumulate sediment over time, and then that farmer can dig out that sediment and put it right back on his field to try to close that loop. It's not going to be like 100% of the nitrogen you put in or whatever, but it's mitigating that a little bit. So yeah, it's definitely in the works. I hope it can be used in the future. It seems to be a good idea. Yeah.
Thank you, Michael. Double thank you. Get ready for your item. Thank you all for stopping. Please have some refreshments. Enjoy the beautiful